Today we'll be looking at the full moon, and we'll look into some details about the moon's orbit and how the phases work so that we can investigate some misconceptions, some misunderstandings that some people have had. Specifically, we'll look at why it is we don't get a lunar eclipse every single month and how it is we can see a full moon at all. The idea goes something like this. So here's the sun, here's the earth, here's the moon. I shouldn't have to say this, but this is clearly not to scale. If we're going to get a full moon, we have to have the lit side of the moon pointing towards the earth. And that means an arrangement like this. The sunlight streams straight toward the moon, but oh look, the earth is going to block it, and the shadow of the earth will hit the moon. We should get a lunar eclipse. Well, that is how we get a lunar eclipse. So why is it that doesn't happen every time? How can we have a full moon without a lunar eclipse? Well, there's a detail that's been missed. That detail is that the moon is on an orbit that is inclined. We say it's inclined. That means the plane of the ecliptic, that is the plane that the Earth orbits the sun around, and the plane of the moon's orbit are at an angle. The moon orbits at an angle of about 5 degrees. Clearly, I've exaggerated that angle here for emphasis, but this should be a 5-degree tilt. Now we can see that when the sun's light shines directly towards the moon, the Earth does not get in the way. That's how we get a full moon without a lunar eclipse. Okay, that brings us to the question of, if that's the case, then the lit side of the moon faces this way, and it does not face exactly back towards the Earth. So how is it we see a full moon and we don't see this little black gap down here? So if we place a little observer here on the Earth, and the observer looks up at the moon, that's where the observer is going to see the top of the moon, and here's the bottom of the moon. And what we're going to see is that the top of the moon is clearly illuminated, but the bottom of the moon is down in the dark region. This circles now the moon. This line represents the line pointing back straight towards the center of the Earth. This line is the illuminated terminator for the moon. This is where the sun is shining. The sun is shining here. It's dark on this side. Okay, this line at the bottom is that bottom angle that the viewer sees the moon from. And we can see that this arc here will be dark. This is the last point that viewer can see, and from here to here is all dark. So the question is going to become, how much of the viewer's sight line is this? First, we know that the angle of this line is at what we'll call phi. That is that angle that the moon is up above the Earth at this time. And this varies up to about 5 degrees. Could be 0, could be as high as 5 degrees. So we'll put that angle right there. And this angle, the angle between from the center of the moon out to the very bottom edge, we'll call that delta. This angle here, we'll call it delta. This is the radius of the moon. The moon is not a perfect sphere, so we'll be taking an average for that. And this is the distance from the Earth to the moon. This line all the way down, going back off the bottom of the screen here. This is the distance from the Earth to the moon. That is also not a circle. The moon's orbit is not a perfect circle, so we'll be taking an average for that too. This makes a right triangle. Right here is a right angle. So we have side, 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 where these two make a right angle. This is the hypotenuse. That means the angle delta is the arc sine of the radius of the moon divided by the distance to the moon. So now we have that angle. Let's call this included angle here alpha. And because this triangle is another right triangle, we can use the fact that this is 90 degrees and this is a known angle phi to say that alpha is 90 minus phi. Alpha is 90 minus phi. Okay, let's call this included angle beta, this angle right here, beta. And we'll see another right triangle. Right here is a right angle. Alpha plus beta makes that angle. We got 90 degrees there, and delta is the angle down here. So we have this triangle, this side, and this side. This one being a right angle, we can calculate that alpha plus beta equals 90 minus delta, or substituting beta is phi minus delta. Let's call this line, this distance along the arrow, all the way down to here. Call that V. And remember, this is a right triangle. So cosine of beta is the Rm divided by the V. That is the adjacent side divided by the hypotenuse. So that's the cosine of beta. So we can simplify that down and solve for V. There's V. We now have the length of that. So that means this little piece right here that sticks out past the circle is V minus Rm. Let's zoom in down there. Let's zoom in down here and see V minus Rm is this little thing here. And this angle is beta again. That's that same angle beta. And this is W. I'm calling this length W. What is that? That is how wide does this arc look to the viewer? The viewer's down here looking up this way, looking up towards here. This distance W is how wide this arc looks. And what we'll see is that we have a similar triangle. We have this triangle is just a little mirror of this bigger triangle. So we can say that the ratio of W over V minus Rm, W over V minus Rm is the same as the ratio Rm over V. So that gives us this equation here, and I'm just going to simplify that to give me the ratio of W divided by the radius of the moon. So I just swapped some terms around and I got that right here. So that gives us something that looks kind of like this. Here's our moon. The top half is illuminated from our point of view, but from where we place the observer, the bottom half isn't completely illuminated. We have this little dark patch that is W. So let's plug in some numbers. Take the average radius of the moon and the average distance to the moon. We can plug those in right here to calculate that angle delta. And for phi, that's going to be the angle between the Earth and the moon. And let's take a worst case scenario for this. The larger we make that angle, the larger this is going to be. So let's take it as if the moon is at its full extreme point, the highest point it can go, which is 5.145 degrees. Remember I said the moon's orbit is inclined at around 5 degrees. We got some extra digits here. It's actually 5.145 degrees. All right, now that we have that, we can get beta, which is coming in right there. We can now evaluate V. Here's V, and let's plug that in. What we're really looking for is this ratio right here. This is the ratio of how much is dark to how much of the moon there is. So how much of the moon is dark and in a length ratio? The answer is right there, 0.003634. That's the ratio of how much is dark to how much of moon there is. So I did some digging, and it turns out that the numbers quoted for how you determine how much of the moon is illuminated is based on area. So we'll say that this section here is 100% illuminated, and this section here is just something short of 100%. So in order to get it to match those quotes that we see of what percentage illuminated, we need to calculate the area of this lit region as a fraction of the overall moon. So the top half completely illuminated, area of a circle, pi times radius squared, so this is a half circle, 1/2 of that. So this section down here is going to be a section of an ellipse. We know this radius is going to be the full radius, but this radius is going to be the moon's radius minus that W. So we'll take the area of an ellipse right there, and we'll take half of that. I'm just going to take the RMs out and write it like this. And now if I add these two together and I get the total area, this is the total lit area of the moon. And we want that as a fraction of what it would normally be. Now, normally we would just say that if it was a perfect circle, we just have pi r squared. So we just take that as a fraction, and so we'll just divide by that, and well, these are going to cancel, and we're just going to be left with this equation here. This is what percentage of the moon is illuminated. So if we take this value and plug it in right here, we're going to get 0.998. The moon is illuminated 99.8% in this illustration. Now I did make a few shortcuts. I didn't account for the fact that the viewer could be in a different place on the Earth. That could make it very slightly worse than this. In reality, I've seen this number go to 997. So the next question. So with 99.8, 99.7% illumination, can we even tell that the moon is not completely full? I went to Planetary Society and I grabbed this high-res image. So I grabbed that 4K photo of the moon from the Planetary Society and I loaded it into GIMP. And let's take a look at it. Here's the moon. And you can see right away that this part is very bright and crisp along the edges. All around here, very crisp, very crisp. That streak is fuzzy here. It's fuzzy around here. And up in this area, you can see some craters that are being partially lit. See right here, this crater is lit around the rim and not lit down in the valley. And there's a ridge back here that has been lit, but the room in between, the space in between, is not being hit by the sun. So we slap a circle. Let me zoom back out for you. Slap a circle, purple circle around the edge of the moon. And the moon is not a perfect sphere, but I did my best to estimate approximately what the equivalent sphere, or what the circle would be if it were illuminated, and that's what I came up with right there. Okay, and you can see right in here, not completely illuminated. So I grabbed another circle, my best estimate of where the terminator line is. Something like that. And this is, obviously this is an estimate, so I'm going to put my margin of error at plus or minus 4 pixels maybe. And my estimate was that these two circles are 14 pixels apart. So these two circles separated by about 14 pixels. So that means there are 14 pixels of unilluminated moon in this image on one side. So we found that 14 pixels of the moon are not illuminated in that shot. That equates to a ratio of around 0.0072. So in this shot, the moon is about 99.6% full. So in this full moon shot, not quite perfectly full. And yes, we can tell if you can get a high-res image of the moon. So let's review what we found out. Why don't we see a lunar eclipse every single full moon? Well, we said the moon's orbit is inclined at around 5 degrees. That means the Earth and the moon don't always line up perfectly. Usually the moon is offset a little bit above or a little bit below the Earth's shadow. When they do line up perfectly, as the moon is passing that point, as it passes the point right that lines up with Earth's shadow, if you have a full moon right then you're going to get a lunar eclipse. So if the moon and the Earth and the sun are not perfectly lined up, then how is it that we see a full moon at all? Well, the truth is, most months you don't get a perfect 100% full moon. What you get is very, very slightly less than perfect. How slightly? The range is from 99.7 to 100%. So many times you're going to see that quoted as simply 100%. And I think we can forgive the authors for rounding off by that last 0.3%.